All right, so this is going to be the last video in the momentum videos. After this, we will do some review. I'll let you guys know what you need to know for the test, and then we will have a test. So the last topic that we are going to talk about is called a ballistic pendulum. A ballistic pendulum is a great example of an inelastic collision. What it is it's a device that's used to measure the speed of a bullet before electronic timing devices were developed. So before we had any cool technology, what they used to do is they would fire the bullet into a block of wood, and the block and the bullet would then swing upwards to a certain height. And if you measure the height of that block, you could then work backwards and figure out the speed of the bullet. So there's a picture down here. I think that you should connect that line and it makes it a little clearer. Essentially, we have the bullet colliding with the block, and then the two of them swing, so the bullet block becomes the dotted line bullet block. So essentially it goes from hanging here. I'm not very good at tracing apparently. And then it swings upwards and it ends looking like this. Of course, for an instant, it'll swing back downwards. But if you know the maximum height that this swings, if you figure out this height h, you can figure out what the initial speed of the bullet was. So it's a little hard to imagine. I have a little toy that I could show you if we were in class, but since that's not going to work, there's a YouTube video that I can show you instead. It is absolutely ridiculous. Not really sure who this guy is, but he has an entire show, and one of his episodes are all on ballistic pendulums. So this is a 5-minute video, but I'm not going to play the whole thing. I'll just play like the first couple minutes, and then we'll jump back to our notes and solve the problem. So get ready for the Idahoan show on ballistic pendulums. It is ridiculous, but it gets the point across.
Well, good afternoon and welcome back to the Idahoan show. I know I haven't uploaded that many episodes lately. I've been awful busy with some other things, and the weather hasn't really been very conducive to outdoor filming. Even today we've had intermittent high winds and more than a few snowflakes in the air, but since when did a little snow and wind stop an Idahoan from doing ballistics experiments? Anyway, today I've got a basic ballistic pendulum for you. The way this works is I've got a target suspended on a rigid arm that swings in a bearing. And as that swings back and forth, it moves the needle on this protractor here. And the needle has just enough friction that it when the arm moves it back, it stays in position. And so it records the maximum angle to which the arm swung. And what this allows me to do is to measure the kinetic energy that was imparted to the target by the impact of a bullet. And there's a variety of things that we can use this for. There's a variety of tests that I want to do with this later on. But for today, I just wanted to try it out by doing some basic velocity measurements. Specifically, I'm going to be shooting a .44 Magnum round, 240 grain jacketed hollow point bullet with, I believe, 18.5 grains of 2400 powder behind it. I've actually already shot that round across an electronic chronograph, and so I know that from this gun, it's shooting about 1600 feet per second, plus or minus about 10 or 12 feet per second. So now I'm going to shoot the ballistic pendulum with it a few times and calculate the velocity based on conservation of momentum, and we'll see how close the velocity measurement that I get from this thing compares to what I got from the chronograph.
All right, so on that slow-mo note, I think we're going to pause it here. He then goes on and he does his calculations, but instead of listening to all his calculations, why don't we just do our calculations? If you really want to see the end of that video, you can just YouTube it, but we'll call it good enough there. So let's look at the numbers that we have going on here for our problem. We are told, we are told that the large block of wood is 5.4 kilograms. We'll label that there. We are told that the bullet is 9.5 grams, which is 0.0095 kilograms. And we are told that it swung to a height of 6.3 centimeters, which is 0.063 meters. We want to figure out the initial speed of the bullet. In order to do that, we're going to work backwards. Essentially, we have 3 time periods. The initial situation of the bullet moving block at rest. Then we have the bullet and the block in the the bullet and the block after the collision before it gets to its height. Then we have the bullet and the block at max height. So bullet moving, block at rest, bullet and block moving together some speed, and then bullet and block at max height. What we can do is we're going to use conservation of energy between points 2 and 3 to figure out the speed of the bullet and the block. We'll call that, we'll do V prime. Then once we know the speed of the bullet and the block after the collision, we can work backwards again using momentum to figure out the speed before the bullet hits the block. So essentially, we've got, so let's say, look at 2 to 3. And what we have is the kinetic energy of the bullet and the block gets converted to the potential energy of the bullet and the block. So 1/2 mv squared equals mgh. The mass for both of them is the combined mass of the bullet block. You could put that in if you want, but it doesn't really matter because it just cancels. So 1/2 v squared is going to equal 9.8 times 0.063. So we have the speed to be 1.11 meters per second. That's the speed right here. That's the speed not of the bullet, that's the speed that the block is moving after the collision. That's not the question. The question is, what is the speed of the bullet? So we're going to look at 1 to 2 now, and that's conservation of momentum. Initially, we have the bullet moving, so the momentum of the bullet, the mv of the bullet, is going to equal the combined mass of the bullet plus the block, I'll call it wood, times the speed that they're traveling. That's the speed that we just found here. This speed is going to go here, and we're looking for the initial speed of the bullet. 0.0095 times the speed of the bullet is going to equal 0.0095 plus 5.4 times 1.11. When you do that, we can find out that the speed is 632.75 meters per second. So knowing that it rises 6.3 centimeters, that means that the initial speed must be 632.75 meters per second. Yay! So there's technically a part B. It says, what is the kinetic energy of the bullet? How much of this energy remains of mechanical energy of the swinging pendulum? It's pretty much saying, is kinetic energy conserved? What is the initial kinetic energy? What is the final kinetic energy? are they the same, or is there energy lost? So, real quick, I'm kind of out of space. Where should I write this? I'm just gonna write it on down here. Don't worry. You hopefully can fit it all on the same page. I wrote too big. So we're gonna go part B. We can figure out the kinetic energy of the bullet. So the initial kinetic energy is 1/2. The bullet's mass is 0.0095 times the speed, 632.75 squared. So the initial kinetic energy is 1901.77 joules. The final kinetic energy after the collision is going to be 1/2 the total combined mass, the bullet and the block, so 0.0095 plus 5.4 times the speed that it's traveling, which was 1.11 squared. That's going to equal 3.34 joules. 1,901 is not equal to 3.34 joules, so kinetic energy is not conserved. We lost 1,898.4 joules of energy. So this is not an elastic collision. Kinetic energy is not conserved. We actually lost a lot of energy. All right, cool. So that is your lesson on ballistic pendulums. I want you guys to do number 15 right now. So this is an example of a ballistic pendulum. It's very similar, but it's working backwards a little bit. I'm going to change the question. I don't want you to figure out the horizontal component. I want you guys to figure out the vertical component, VERTIC, vertical component. So figure out the height that the pendulum is going to swing if you know the initial speed. So we're kind of working the other way here. Check your answers when you get it. Actually, I'll tell you the answer. You should get 0.0668 meters. If you don't get that, then we got some issues. But hopefully you do. Give it a go, and let me know if you have any questions. All right. Have a nice rest of your day.